This video is on functions and specifically on composite functions and inverse functions. And I've got this first bit here on composite functions. This is on the second page of the addition of ordinates micro summary, and it's just a little bit on composite functions. So a composite function is a function within a function. So if you've done chain rule in calculus, it's kind of the same notion that we're dealing with here. So it's a function inside a function. You can represent it as f of g of x. In other words, g is inside of f, or g of f of x, where f is inside of g. So we can also represent those like this. Fog, these are often called fog and goff. So fog and goff, where the little circle is indicating a composite. So that's what that means, and that is what that means. So if you ever hear anyone saying fog or goff, this is what they're talking about, composite functions, where a function is inside another function. So a couple of things, so notation-wise, we've dealt with that. It's important to note that the domain of a composite is the same as the domain of the inside function. So what we're almost doing here is let's say we've got I always think about it as a conveyor belt system at a factory. So you've got a conveyor belt and it's going through two different processes. So what we're putting in here is x values. We're putting in x values into f of x. So this is for, this would be for this one. So we're starting with f of x. F of x is in the middle. So we're starting with that first. We put x values into f of x, and y values is what come out. Now those y values have to then turn into x values for the g of x, and out come y values. So with g of f of x, we can think about it as subbing in values for x, then we get a y value, and then that y value becomes the x value for g. If we imagine g of x, the y value of f of x would become the x value for the g of x. So this is the conveyor belt system that I think about. So the domain of the whole thing is just whatever values we can put into f of x. So the domain of f of og or f of g is the domain of the inside one. So the range of the whole thing, the composite, is found by graphing it over the domain, because the y values that we get coming out here, which is going to be the range overall, so this one's the domain overall, which is the domain of the inside one, but the range overall is going to depend on what x values we put into here, which is obviously going to depend on what y values come out of the first one. So the range is not often just easily observable. You've got to graph it or conceptualize it of what's happening overall. Now, this is the most important sentence here, this fourth one. It says f of g only exists if the range of g is a subset of the domain of f. So f of g only exists if the range of g is a subset of the domain of f. So that's that there. Now we can write it the other way as well for goff. We can say the range of f, it will only exist if the range of f is a subset of the domain of g. Now if we have a look back at our conveyor belt system, actually I might just draw that one more time. Now we'll deal with goff here, so that's this one. So f is the inside one, g is the outside one. Remember, we're putting x values in here. We bring out y values that become x values into the second one, and then y values come out again. So this will only exist if these two match. In other words, if the range of f, which is the y values that come out of the inside function, fit inside the domain of g. So let's think about an example where that wouldn't work. Let's say our f was x squared, but our, sorry, not x squared, let's just change it to x. If our function of f is just x and g of x is the square root of x, we can have any real numbers going into there, all real numbers, and all real numbers coming out again. So our y values from y equals x, our range is all real numbers. Our domain is all real numbers, and our range is all real numbers. But our domain of this one is not all real numbers. We can't have negative values here. We need positive values or 0. There's a better way to draw that. Just hang on a second. Let's get rid of that. So our domain of this one, this y equals root x, is just 0 to infinity. But let's say we put x equals -5 into the first one. We're going to get y equals -5 out of the first one. But if that becomes an x value, that doesn't work with this function. So in this instance, the range of f is all real numbers, but the domain of g is 0 to infinity. So the range of f is not a subset of the domain of g. So in this instance, GOF doesn't work because the range of f is not a subset of the domain of g. In other words, the range of f is bigger than what the domain of g can handle. In other words, the range of f does not fit inside the domain of g, and that's really important with composite functions. We need to ensure that the range of the inside function, let's try and learn how to spell that word, the range of the inside function must be a subset or must fit inside the domain of the outside. And that's really critical. That's the most critical sentence in this summary, that it only exists if the range of g, which is the inside function, is a subset of the domain of f, which is the outside function. So that's really, really important. Now, the last sentence here said the domain of g can be restricted to allow this to be true. So we can ensure that GOF works here as long as we restrict the domain of the inside one so that the range of the inside one fits inside the domain of the outside one. So in other words, if we go back to that conveyor belt system, this was y equals x, this was y equals root x. We have x values going in here, we get out y values, they become x values that go into here, and then we get y values out. So this is, in other words, y, or let's use h of x equals, so we've got f, no, that was g of x equaling x, f of x equaling root x. So we're putting this one inside the other one. So in other words, it just is root x. Because if we put x in there, it's just root x. At the moment, our all real numbers coming out doesn't fit inside there. So how can we limit that so that this range is a subset of the domain of this one? So our range, our domain of the outside one at the moment is 0 to infinity. Our range of the inside one is all real numbers. We need to restrict the range of this one to be this at the very largest. So how can we make the range of y equals x equal to 0 to infinity? Well, all we need to do is change the domain so that the domain is 0 to infinity. So we're changing the domain of f. Remember, f of x was x. We're changing the domain to 0 to infinity. So now let's have a look at that conveyor belt. So remember, we had f of x here equals x, g of x here equaling root x. Now, if we're restricting what goes in here, this is the domain of f, if we're restricting that to 0 to infinity, then the range of f will also be 0 to infinity, and the domain of root x is already 0 to infinity. So we've now matched that up. We've now made that work. So by restricting the domain of the inside function, because remember we're dealing with g of f here, which is gof, by restricting the domain of the inside one, we've now made this connection work. So now we can get a function that actually works, because originally this didn't work because the range was not a subset of the domain of G. So we've changed the domain of F to ensure that the range is a subset of the domain of G. So hopefully that makes sense. Let's consolidate this by looking at some questions from the textbook. So the first couple of questions simply say, and let's bring that next door. First couple of questions just ask you to write it as a composite. So we can do that. Question 1a says express this as the composite of two functions. So we could make f of x e to the power of x and g of x x cubed. So then it would be g would be inside f, so it would be f g, and that would be what we get here. So that's the composite of those two. G, that is going to be placed where x is on the f function. So that's all question 1's doing, and it's very similar to the chain rule with calculus, finding what u and v is. So if you're doing, if you've done calculus, then that'll be a link there. Let's have a look at question 2. Question 2 says, let f of x equals 4e to the 3x, and let g of x equals 2 over the cube root of x. And then it says our domain is all real numbers other than 0, so that's obviously with g. Find, now let's skip those two, we'll come back to those, f of g. So we need to find f of g, where f of x is 4e to the 3x, and g of x is 2 over the cube root of x. So f of g means put g where x is for f. So we're going to get 4e to the 3, and instead of x here, we're going to replace it with all of g. Like that. So f of g is going to be 4e to the 6 over cube root of x. Like that. So that's all you're doing for that function. If we have a look at number 4, we're just doing the same thing. So we're finding rules, but this time we're also finding the range and the maximal domain for them to exist. So this is sort of tying it all together. Let's have a look at this one. So question 4, we've got g of x equals x squared. And they're giving us each one, so let's do A. In A, they're giving us f of x equals 3 sine 2x. So 1, find the rule of Fogg and Goff. So Fogg is just g inside of f, so it's 3 sine 2x squared. So all we're doing for Fogg is we're placing that where x is there. And Goff, we're just placing this where x is on the other one. So it'll be 3 sine 2x all squared, and we can leave it like that, that's fine. So there's the rules for Fogg and Goff. And 2 says find the range of each of them and state the maximal domain for each of the composite functions to exist. So let's start by doing the domain of f and the range of f. This is a really good way to do this. The domain of g and the range of g. So the domain of f is over here. The domain of f is all real numbers. We can put any x value in that function. So sinusoidal functions or trig functions have domain of all real numbers. The range of f, now we know the range of a sine value is the center line plus or minus the amplitude. So this doesn't have anything added or subtracted on the end, so the center line is at 0, and the amplitude is 3, so it's going up 3 and down 3, so the range will be -3 to 3. Now looking at g, we know the domain of x squared is all real numbers, but the range is 0 to infinity. So obviously knowing this stuff relies a lot on your knowledge of all of your functions that you know already. So that's the domain and range of each one. Now we have to think about the range of the composite functions. So before we do that, let's think about whether they exist. Fog, we're relying on the range of G being a subset of the domain of F. So the range of G fitting inside the domain, that's the wrong way around. The range of G fitting inside the domain of F. So that works. This one we want the range of F to fit inside the domain of G. That works as well. So both of them exist, so that's fantastic. Now what's the maximal domain for them both to exist? Well, they both already exist, so remember that here said the domain of a composite is just the domain of the inside one. So the domain of fog is just going to be all real numbers because that's the domain of the inside one, and the domain of goff is just going to be the domain of F because that's the inside one. So both domains here are all real numbers. So let's have a think now of what the range will be. So what we can do here is think about our equations up here. So what would be the range of this one? Well, this is just going to get x values. So 2x squared is just going to give pretty similar x values to what we have here. So the range is just going to be the same as what the range of this original one would be. So I'm going to suggest that the range of this is still just -3 to 3. So let's just think that through. What can't we get here? We can't get any negative values. But all that means is in terms of the unit circle, we wouldn't be going in that direction. But we'd still get every single positive answer. So we can get every single answer this way. So we can get all real numbers there in terms of positive answers. Sorry, not all real numbers, all positive or 0 real answers. So therefore, it's just going to take on the same properties. So that would be our range there. And for this one, we're going to get all of our y values that we would here. So this one's -3 to 3, but this time they're all going to be squared. So if we think about what the result of squaring this interval would be, it would be 0 would be the smallest we would get, and 9 would be the largest. Because -3 squared is 9, and +3 squared is 9. And then we wouldn't get any negative values because we're squaring it, so therefore it would just be 0 to 9. So there's the range of goff, and there's the range of fog. And remember it said here the range can be found by graphing it or by conceptualizing, which is what I've done. So that's composite functions. So now with inverse functions, now inverses is probably something you've done plenty of times before, so I'll just recap it. We know with inverses what we're doing is swapping x and y and then rearrange to get y by itself or as the subject. So we get y equals. Inverses, we write little -1, so it could be f -1 of x means the inverse of f. G -1 of x means the inverse of g. So if we have a look at question 2, question 2 says let f of x equals 4e to the 3x and g of x is 2 over the cube root of x. So that's one we did C and D for before. Now we're going to do A and B. So the inverse of x, we would swap x and y. Now remember the f of x replaces the y. So we'll have x at the front, 4e to the 3y. Then we need to rearrange. So we'll get x over 4 equals e to the 3y. Then we'll need log base e of x over 4, which is 3x. Didn't change that to a y there, so that's a mistake. Just a habit. That's a y, which means that one's a y. And then we need to divide it by 3. So we'll get a third log e of x over 4. So that's the inverse, and then we would write it with the correct notation. So we would go f -1 of x a third log e x over 4, and that's the inverse of f of x. The inverse of g of x, so again, g negative 1, we'd make it x equals 2 over the cube root of y. Then we can swap this over there with that, so we'll get cube root of y equals 2 over x. If you're not sure about the maths there, just to recap, we could multiply that by x and then divide the x across. So you can just swap them. It's like saying 6 equals 12 over x. You can swap the x and the 6, so we'll get x equals 12 over 6. So it's the same, and that's completely okay mathematically to do that. So you don't have to multiply and then divide. You can do it in one step. So now the opposite of the cube root is cubed. So we would get 2 over x cubed, and we'd get 8 over x cubed, like that. So that's the inverse of g is 8 over x cubed. So that's how we do inverses. So that's pretty easy, I would assume, and I'd assume you'd have enough knowledge to do that. Last thing I wanted to discuss is this stuff here, the strictly increasing and decreasing. This is a lot easier than it sounds sometimes. So let's just go through it. So a function f is strictly increasing if a bigger than b implies f of a is bigger than f of b. So all that's saying, now that can be difficult to get your head around, but all it's saying is if we're moving from left to right, in other words, if a being bigger than b, so if a is on this side, so if we have a graph and we've got a here and b here, so that's moving from left to right, in other words, then the y coordinate when you sub in a is bigger than the y coordinate when you sub in b. So in other words, if we're moving from left to right, we should always also be moving from top to bottom. So that's what strictly increasing means. In other words, it can't come back down again. Once it's going up, it has to continue going up. That's what strictly increasing means. It means going up always. Strictly decreasing is just the opposite. It's going down always. So don't confuse this. It's very straightforward. Strictly increasing means going up always, and strictly decreasing, going down always. Important to note here that if it's strictly increasing, then it's 1 to 1 because it'll pass the vertical and horizontal line tests. Same with strictly decreasing. And then this one is just saying if it's strictly increasing, then the inverse is also strictly increasing. Same with decreasing. So that's, don't overthink strictly increasing and decreasing. Let's just find a question to practice that. There is one here, I'm pretty sure. Here we go, for 3. For either function f, find the inverse, for each function, find the inverse function and state whether they are strictly increasing, decreasing, or neither. So I've done the inverse, so I'm not going to do that now because I've just done an example using question 2. But let's have a look at question C, x to the power of 5 over 2. X to the power of 5 over 2. So what we're wondering here is this strictly increasing, decreasing, or neither? So we can use our calculator to determine what's going on with this graph. So we'll go to the graph, we want x to the power of 5 on 2. And we've got this graph here. Now we know the domain already is from 0 to infinity. And all we want to know is if it is strictly increasing. We can see it's definitely not strictly decreasing. So we just want to know, is it going up always? As we get really large values, it's going to continue going up. I want to see in here what's going on. So I'm going to zoom in a little bit here between 0 and 1. And I just want to see if at any point it's going down again. And we can see from the graph that it is continually going up from 0 all the way up. So we can say that this one is strictly increasing. Hopefully that makes sense.